So today we have Zach Weiner visiting from the Perimeter Institute. Zach did his PhD at the University of Illinois with Peter Adshead, did a postdoc at the University of Washington before taking his current position at the Perimeter Institute. He's here today to talk about coupled scalars across cosmic history. I know that you'll be talking some about neutrinos at the end, which is the work of Zach's I'm most familiar with. And as I said when introducing Marlena last week, despite having written like 3 papers on how neutrino masses are constrained from cosmology, back in April, I started following the DESI results in April, started thinking about what's going on with that data set, and realizing the story wasn't complete, and there were some things I didn't understand, and we started working on this, and we finally understood it when Zach explained it to us. So thanks for visiting us, Zach. I look forward to hearing your talk.
Thank you for the very generous introduction, and yeah, thanks for having me. It's after having some temperate weather for a few years in Seattle, as we discussed it earlier, I'm glad to get a break from some California sunshine, a break from the snow in Ontario. Yeah, so I'm going to be talking about work. I did that magical thing where the paper is on the archive today, and I'm talking about it. So, like, first paper on this topic was last May, and that was more focused on the cosmology analysis. And then this new paper, literally out today, is more about the particle theory underlying the relevant models and other signatures. And so I'll be talking about both of these, and because, as Lloyd alluded to, because some of the work that went into this ended up being the way that I, at least personally, gained some insight on neutrino mass, I'm going to try to draw that connection at the end if it's not too ambitious. And I'll say, like, in support of that goal, I've tried to keep things at maybe a bit more big picture, so please feel free to slow me down if I'm making points too quickly, or if you want more details or anything. And of course, I'm happy to talk more about details at any time. And then I'll just call it, this is work with Masha Berryakta, our particle theorist at UW, and Olivier Simon, a current postdoc at Princeton. Okay, so the premise and like the motivation for us thinking about this class of theories of coupled scalars is a long history of usage of of observations of the CMB anisotropies to measure and constrain variations in the fundamental constants over cosmic time. It's been nearly, I guess, 2.5, 3 decades at this point. And a lot of this work, giving great physical insight into the cosmological signatures, was not especially grounded in concrete models and in the actual particle theories or microphysics that would give rise to those scenarios. And particularly given that this class of theories has become even more exciting of late because of possible connections to the Hubble tension, specifically the well-explored possibility that were the electron heavier at very early times, the sound horizon, I'll talk about it in more detail, but the sound horizon would have been smaller than in standard cosmology, which would have then led us to infer a Hubble constant from CMB data more concordant with that which is measured directly. And so our goal was to put some concrete scenarios to this phenomenological modeling to be able to assess things like consistency with other probes and consistency, on a theoretical basis. In particular, to tell the story of how this transition from some, percent level, say, shift in the fundamental constants that in the standard, phenomenological treatments is just supposed to be time independent but different at early times. To tell the story of how that, settles down to the, level of variation that would be allowed at the present day, or rather, how the electron mass took on its present day value. I'm going to focus on electron mass for concreteness for maybe like 60% of my slides, but a lot of the same considerations apply for fine structure constant, so we specifically considered couplings to the photon and couplings to the electron. Okay. So I'm going to try to discuss what are the actual particle theories that can do this job. Do they have additional phenomenology that I need to worry about? How do I combine searches from other probes, from other other things that tell me about the values of fundamental constants? How do I combine with that information? And then I'll also talk about the cosmological constraints on the specific scenarios that we consider. Okay. Yeah, and then if I have time, I'll tell you what this teaches us about neutrino masses. Okay. Any questions before I start? All right. So I'm first going to motivate on a kind of a general theoretical basis why we should care about having models. Aside from the success of particle physics as an endeavor in understanding reality, just like why do we need to think about microphysics when studying these types of scenarios? So if I want to do the simplest, most constructive thing to make the fundamental constants vary with time, you could just literally promote them to, say, the electron mass to a dynamical scalar field that depends on spacetime, and give it the standard, canonical Lorentz invariant kinetic term. And I mean, the stupid thing, the obvious thing is that you have an interacting theory, and so whatever dynamics you take on for this electron mass as a function of space-time are necessarily going to be affected at some level by those interactions. So specifically, there's a cosmological abundance of electrons. Those are not necessarily irrelevant to the effective potential or the dynamics of the electron mass in this case. Kind of the physical intuition that you should carry with you is that if I allow the electron mass to vary, then I can lower the energy of the system by reducing that mass. And so there has to be some, energetic driving towards that lower energy state. And so fundamentally, that's something that I can't avoid, or at least it takes steps to show that you can neglect that.
Before you,
Yeah.
So this is sort of ridiculously pedantic, but I'm just curious about. So when I see this, I'm tempted to use the term demote rather than promote. Fundamental constant sort of has a certain status.
Yeah.
And then dynamics to me feels a little more messy.
Yeah. Well,
I'm just curious how you feel about it. So I don't have a.
I'll gladly match or exceed your pedantry.
Oh, that'll teach me.
I mean, the electron mass is not fundamental.
Right.
And so, for those who are wondering, I really will be talking about modulations of the Higgs-Yukawa coupling and not the Higgs-Bev, which the distinction does matter. I won't explain why in my slides, but it's in the paper and I can tell you about it. But yeah, so what are the fundamental degrees of freedom even of a theory depends on your energy scale, and so the electron mass is just it's a thing. Of course, you already know. It's also kind of a lie to say that I'm promoting, because the electron mass depends on the Higgs-Bev, and that is a dynamical thing. So in truth, at least the mass scales of the standard model are dynamical variables as well, just not in its vacuum state. So that's how I feel about it. I don't know if that answers.
Yeah, no, that's good.
Yeah. Okay. Of course, this is a ridiculous way to go about things, but it's just very constructive, easy to see in general terms. This is a point that's not going to depend on, in principle, it's not going to depend on the model that I end up writing down. In practice, of course, we introduce a different field, a scalar field, that will be the Sperling phi give it its own potential, and I'm only going to talk about quadratic potentials, so just some bare mass term for the scalar. This I'll say this up front, but if it gets confusing later, ask me and I'll say it again. But this curly phi is basically the dimensionful scalar field, like the normal thing that we write down in the Lagrangian in Planck units. And that's useful because it like normalizes its strength relative to gravity in some sense. So it's kind of just like the variable you would choose if you wanted to make this scalar look a little bit like a graviton. And that's just for convenience, just so I don't have to have factors of M Planck floating around. Okay, and this is really just notation, like, instead of electron mass depending on space, it depends on space via the scalar field, blah, blah, blah. There's, write down a function to parameterize that. The real thing to remember from the slide is that there's, for the electron mass, there's a coupling to the electron's mass term. For the photon coupling, there's a coupling to the photon's kinetic term. And then the specific forms of these coupling functions, these blue G's here that I'm going to consider are just, a series expansion, and I'm going to focus on the leading order terms, counting on some degree of like perturbativity in this expansion. So linear and quadratic couplings, you'll hear me talking about both of those, and that's it going forward. Okay, and actually more than that, I will end up focused for reasons that the first part of this talk is meant to motivate. I will be focusing on quadratic couplings, and so some of the next slides will be specific to quadratic couplings. But again, like the general picture, the picture is more general. It's not so specifically tied to quadratic couplings, but that's what we work with for completeness, and for deeper reasons that I'll explain. Okay, so this effective potential from the interactions with standard model particles, like actually kind of easily can do things that you didn't necessarily want it to do. So just like to reiterate, I'm trying to model build in essence this picture where the scalar now is not doing anything until some point after a combination, and then it does something. And so I'm trying to tell you, one, how easy is it to get it to do nothing here, and then how can I, like, what are the some things that I can get it to do later? So the first question, like, can I keep it frozen until recombination? Well, even without considering like the bare potential for the scalar field, generically, no, I can't. As you go from this dark purple to this yellow curve, I'm dialing up this coupling coefficient. This coupling to the quadratic term in particular, and this is just showing you that like the stronger I make the interactions, which nominally I might use as a way to increase the signature in CMB data, the more the effective potential from the electrons in this case. Actually, this applies to both, but the more the effective potential from the interactions with the standard model plasma have an impact on the scalar's dynamics, and so you can place some limit on viable couplings. Again, there's like conventional factors around here. I don't want to get bogged down in the details, but there is some level of coupling where the scalar just can't stay frozen until recombination, and so I need to be living in this moderately weakly coupled territory in order to achieve that phenomenological picture that has been of interest.
In this territory where you these darker curves.
Yeah, like like in practice, I might say, okay, I don't really care. Like I'm willing to. Okay, so like this is the scalar field amplitude, and so this is like some measure of the shift in fundamental constants, and so maybe I'm willing to like allow me to be mismodeling, to like be neglecting a 10% shift in the shift, if you will. And so like some of these blue curves are okay, but certainly like this green one that's already completed an oscillate, or it's already crossed through zero by the time of recombination, is not going to be well described by a model that assumes that the variation in fundamental constants was time independent before that point.
And the size of the variation in electron mass that we're interested in, can you remind me of that?
Order percent. yeah, we'll get more quantitative. Any other questions? Okay. All right, so now I know like I can't have too strongly coupled a theory, otherwise I don't get the dynamics that I want, or at least I don't get the dynamics. There's nothing wrong with this a priori, but I will just say now that like the cosmological signatures of this regime we have not studied, something we hope to do in the future, but we are trying to stick with, for the purpose of this talk and the 2 papers that we have on so far, stick into this regime where the scale remains effectively frozen. Okay, so why is this the problem? Why can't I just make my theory weakly coupled? Well, the size of using lambda as a stand-in for whatever parameter, so fine structure constant alpha or the electron mass, the degree of variation at any time is, as I parameterized, as I just chose a few slides ago, is this coupling coefficient, this d, and then the field to some power. So in the case I'm taking squared. Now the field squared is basically what the scalar field's energy density is. And so if I multiply and divide by factors of m Planck and blah blah blah.
Zach, sorry, what is lambda?
Sorry, lambda is any parameter. It's like alpha or electron mass. Yeah, it's just lambda is what I'll use when I want to refer to both on equal terms. Yeah, sorry about that.
Sorry, I also have a quick question. So on the previous slide, when you were talking about keeping phi frozen, that's being frozen in by some friction term.
Yeah. So really what's happening here is that there's a competition between Hubble friction and the effective potential from matter, and the larger I make this coupling, the earlier the effective potential wins. And so I need to keep the effective potential low enough that Hubble friction wins at least until after recombination. Okay, so variation in any parameter lambda, just think of electron mass if you like, I can essentially rewrite as the product of, again, the same dimensionless coupling, and then more or less the fractional contribution that the scalar field makes to the universe in terms of energy density. So, like specifically, I can exchange. I can just write my parameterization of the signature, say the variation in fundamental constants, as this coupling, which controls the things like the effective potential we've been talking about, and the relative contribution to gravity. So the degree to which gravitational effects are important. And so if I want this to be order percent, then, and I can't make this bigger than order 1, then this one's going to be order percent, right? So I have to make one of these two things large in order to get an observable signal. And by neglecting both of these effects, the phenomenological analyses from the past are essentially restricted into this regime where really you can't accurately describe variations in fine structure constant or electron mass greater than ish percent. This is a illustrative plot; it's not quantitative, of course. But so I can choose either axis to go in if I want a large signal, but I've already told you why I don't want to go in the strong coupling dimension, because I'm trying to keep my dynamics frozen at early times, and so therefore I'm pushed into parameter space in which I need the scalar to contribute to, say, the total dark matter density of the same order at least as how much it changes the fundamental constants at early times. So this is again, there's I've taken a relatively generic, but obviously particle physicists, we can play games, but without playing any ridiculous games. I've basically worked myself into this general corner of parameter space that already tells me, just on theoretical grounds, that I should have another effect when I'm trying to model build these theories of varying constants. Okay, so the next part I'm going to get a little bit more into the viable space of models by specifically considering other searches, so everything other than cosmological data. So you'll have to hang on to this thought until I get to that point. Yeah, any questions on that before I proceed?
Sorry, so why do we want electron to have a different mass before recombination? What so?
Yeah. So I'll reiterate on this in part 3, I think, which is cosmology, like the cosmological signatures. But really, so first of all, the prior phenomenological study has just been of exactly that type of situation, where I suppose that the fundamental constants were different at early times, but not evolving, and just constraining that. And so, like, first we're just trying to work out what are the actual, like, particle theories that work is telling us something about. Second, that you might, like, the second reason why current data might actually be hinting at that being like a true feature of reality rather than just something we can constrain is the Hubble tension.
Okay.
And I'll touch on what that connection specifically is. Okay, so the way in which I'm going to try to craft my cut down on model space a bit more is by considering other probes of varying constants at different epochs.
Yeah.
So the earliest probe that we have is nucleosynthesis.
I just asked Lloyd if you'd mentioned BBN yet.
Do you want to guess what the next slide is?
I gotta wait for the last minute.
Yeah. Okay. Great. So yes, BBN. If you mess with fundamental parameters, then naturally you're going to mess with standard model processes, and what controls the main observable, which is the helium yield, is there's electroweak freeze out and blah blah blah. But largely it's just how much neutron decay happened before nucleosynthesis actually occurred. And so if you change the masses of the particles involved in those interactions, then naturally you're going to change the rates, and therefore the amount of neutron decay that occurs at a given fixed time. And so this tells us something about the values of the fundamental constants at those early times as redshifts 10 to the 9, relevant to BBN. And you can just do something very simple and take the theoretical expectation, which is predicted in the standard model to be this 0.246 number. Compare that to the PDG's summary of current experimental measurements, and then just convert the difference between them and the error bar into a measurement of the fundamental constants at that time. And we do this just by using some not especially sophisticated, but half pencil paper, half computer based calculations of how sensitive the helium yield is to alpha and the electron mass. I can give more details, but the point is that this percentage level measurement of the helium yield gives, unsurprisingly, percentage level measurements of these two fundamental parameters. And again, that's applicable at high redshift. Okay, Andy, now's your time to guess. Okay, we're gonna go to late times now.
This one off.
Yeah, we're gonna go to late times now. A shockingly good way that we have of measuring the fundamental constants is so-called quasar absorption lines. So this is just where you have some bright, distant object, like a quasar, whose light passes through on its way to us, passes through some molecular cloud, excites some atomic or molecular transitions that have particular dependencies on the fundamental constants. We measure those lines. They're very, very good measurements. You compare them to analogous measurements in the lab, and then turn those into constraints on the fundamental constants, and that ends up giving part per million level constraints at redshifts between 1 or lower, and actually for fine structure constants they go as high redshift 7 or 8. But yeah, we get very tight, exceptionally tight constraints on variations in fine structure constant and electron mass over redshifts 0 to 10 ish.
A long time ago, there was a group that claimed they analyzed this and they found evidence that alpha varied. What happened to that story?
So if I know being young, I only read about this in retrospect, but I know that there's some like evidence for like a dipole in the sky of alpha. That's the thing that I remember being. And as far as I know, that particular claim is not yet settled. I think there are a number of like spectrographs that will give us a lot more data in the.
This was about calculating 10,000 atomic and molecular lines and then doing some bit to them.
Yeah. No. Yeah. Okay. So.
Yeah, this is some Australian group.
Right.
Yeah.
Can't remember the guy's name.
So there's definitely a claim of spatial variations that I know.
This was time variation.
This is
Yeah, so the time, so that might have been, there was some wavelength calibration issue that was realized around a decade ago that was biasing some of these constraints. And it's been a long time since I looked at this literature, but I think that might have been resolved by throwing out a bunch of old measurements that were affected by this issue. And then since then, the analyses have taken care of this particular calibration issue. That's the best that I remember.
And these part per million constraints, they're from a small number of lines or a large number of lines?
In the analysis, they're using more like a bunch of lines to I think they use Lyman alpha lines to get the redshift, and so like they have to jointly fit these things to back them out. I think usually the constraint on alpha and ME itself is coming from one specific line, but I'm actually I could be wrong. I'm not so sure. Each of the individual measurements I'm showing here, though, is like a different absorption event, so like a different molecular cloud thing. And the redshifts are like the redshifts at which those clouds are. Okay, thanks. So here's the picture. I've got, so this is like a symmetric log plot, and I've got percent plus or minus percent wiggle room from BBN at very early times, and then this is not a constraint. This is just showing where I want to still have an observable signal at recombination, redshift 1,000 or so, and then here are the quasar constraints. And again, since this is like a log plot, these are like very tight constraints, not 10 to the minus 5, 10 to the minus 4. So what I want to do is something like this. I have some like maximum degree of variation of BBN. I just hang on to it until after recombination, and then I make it go away. So knowing something about what scalar fields do, which I'll talk about more in a second. I basically need to arrange for dynamics for the scalar field responsible for this to not happen until Hubble is like below 10 to the minus 29 eV. So that was there a question? That basically puts me in the territory of not being able to use dark matter to do this, because dark matter, scalar dark matter from the misalignment mechanism, so such as some homogeneous displacement of a scalar field from its vacuum expectation value as a way to make dark matter that would become dynamical given current limits. It would become dynamical around here. So I'm necessarily going to be talking about hyperlight subcomponents of dark matter. So that we already know pretty much, and the other question is how much redshifting. So like what do I have to do to get this fall off to be enough to satisfy the quasar absorption constraints without getting rid of my signal at recombination.
And then there's laboratory constraints.
Yeah, that I'll get to next, but yeah, you'll see why they're not on this plot. Okay, so let's answer this how much redshifting question. There we go. So solving the Klein-Gordon equation, again in this misalignment scenario, you know that when Hubble friction exceeds the curvature of the potential, so the scalars bear mass, a free scalar field is just frozen. That's this regime. And then once Hubble drops below the mass, the scalar begins oscillating with a decaying envelope that goes like 8 to the minus 3 halves, the blue. So let's plug in that exponent, that e to the minus 3 halves, onto this plot, considering just a linear coupling, the first thing that you might want to try. And, oop, too bad. It's like, again, this is just an illustrative plot, but there are measurements here that are way, way tighter. Again, this is a log scale. Then what I can do if I just extrapolate e to the minus 3 halves from recombination being percent level to these redshifts. So I already know without doing any hard work that linear couplings, the constraints on those are going to be dominated at least by quasars, if not other probes. And in fact, there is one other probe, a laboratory probe, that is even more severely constraining. And this is tested the universality of free fall for the equivalence principle. The long and the short of it is that new scalar fields mediate new forces in the same way that the gauge bosons of the standard model do. And we can test for those by using different materials with different effective charges under this new scalar force, and testing their free fall towards Earth, for instance. What this ends up doing is giving us like a 10 to the minus 3 constraint on the coupling, and moreover, like very powerfully, one that is independent of cosmology. The thing about linear couplings is that the Earth itself, being charged under the scalar field, sources of scalar field profile in the same way as a point charge sources a electromagnetic potential. And so it doesn't even matter that you have a dark matter background. Just the mere fact that the Earth sources a scalar field profile means that you necessarily have a fifth force, even if you don't have a cosmological abundance. And so this 10 to the minus 3 constraint there's nothing I can do about it. This is like the whole game behind screening in scalar, scalar tensor theories and all that, is to hide this effect. And we can't do that. So that's another reason why that's two reasons why linear couplings are no-go for visible phenomenology at the CMB. Okay, so if not linear, then let's do quadratic, and indeed,
Even if you have a quadratic coupling, so you have some Z2 symmetry, and at some point that's broken, and wouldn't you generate a linear coupling anyways in that case?
that would depend on the details. I mean, there are models that, as I referenced on there, there are models that give you an effective Z2 symmetry or suppress the linear coupling by a few orders of magnitude. That's not to say that they are going to end up being natural. Feel free to grill me on that if you like. But yeah, we're essentially assuming that there's just the Z2 symmetry that is going to eliminate this linear coupling if you are, from an effective field point of view. And so squaring that a to the minus 3 halves gives us a picture that does seem like it could be viable, simultaneously compatible with quasars and EBN, while still giving me something going on at recombination. Okay, and then I have time. Slide. Okay. So there's still laboratory probes, like a quadratic coupling still can generate a fifth force. The problem for the signal is that now I've got factors of the background field that enter, just because I no longer have a direct source term in the Klein-Gordon equation from a linear coupling, but instead there's a nonlinear interaction, and therefore the local value of the field from its cosmological or galactic profile enters into the signal. Since the scalar fields in Planck units has to be much smaller than 1 at the present, this generally suppresses the signal. And so the constraints get much weaker. Actually, it's even worse than that. So in the mass range that we're considering, the scalar field becomes dynamical. It starts oscillating when the universe is, like 100,000 years old, or no, like millions of years old, maybe 10 million, 100 million. that's a very slow oscillation period compared to like our lifespan or the duration of any experiment, but it's very fast compared to the age of the universe. And so if the problem essentially boils down to I have no idea where in the scalar's oscillation, where the scalar is in its oscillation today. It could happen to be at a node, and because like we only know the age of the universe with say percent level precision, we can only like I have to marginalize over the possibility that the scalar is anywhere in its period, and that turns out to penalize late time bounds that are very short in duration compared to the scalar's period, parametrically with mass. Yeah.
What about like geophysics or solar physics or something?
So we have I won't talk. I don't have a slide on it, but we do talk a little bit about like stellar pooling bounds, and those turn out to be those are really weak.
Okay.
Yeah.
So I'm a little confused about this last point because those oscillations would be in the background field.
Yes.
And the measurements they're talking about involve the difference between the background field and the field generated by the Earth. So doesn't that mean that it would take a very odd coincidence for the background field to match in such a way that that those two cancel?
So it's not actually quite that difference. It's more that another way to think about it is that I've got think of like in the method of like background fields, a quadratic coupling can be expanded to a linear coupling where the background field is now just absorbed in my my vertex vector. That's just putting this phi here. And so it's necessarily a multiplicative part of the signal. And so then therefore the signal does oscillate with time. Yeah, the space dependence is separate, but it's multiplied by the time dependence.
Okay.
Yeah.
So if this field is oscillating short compared to the lifespan of the universe, long compared to our lifespans, would we get a pretty big spread of its influences if we look at light coming from distant stars or different galaxies based on like redshift on the scale of a few 100,000 years, a few million years?
So I totally glossed over this when I discussed quasars for the sake of expediency, but yes, like that has to be accounted for pretty carefully. So quasars are like also essentially an instantaneous measurement, at least individually, because what's the light crossing time of one of these clouds? I don't know, but it's not going to be that long. But like the benefit. So yeah, there's two solutions to this problem. One, like wait a really long time, observe a full period of the scalar. That's why we can do these probes for dark matter, because it just so happens that ultralight dark matter, 10 to the minus 23 eV, is like a year in period. So we can just directly observe, one or multiple oscillations. But your other option, as you hint at, is to have multiple observations that are spaced in like many periods apart, and you need astrophysical to get millions or billions of years of separation. You need something astrophysical, and that's what quasars do. So it's actually only the fact that we have a handful or a dozen or two measurements of these quasars that are well spaced in redshift that we can actually get a robust constraint that is competitive. And there's details about making sure that there's analysis details that you can read about in the paper that largely it works out.
Okay, so we need observables on the scales of like millions to billions of light years. Is that correct?
Yeah, it depends on the mass. So for the masses, the masses that do this they're squeezed between 10 to the minus 29 and 10 to the minus 32 eV. So yeah, and those are between like million year periods and nearly age of the universe periods.
Got it. Okay.
Okay, great. Thanks for the questions. Any more? This also kills atomic clocks. I'll just leave it at that. So to recap, and I'm going to show the constraints in a second. But just to recap, like just by looking at all these complementary probes, like test the equivalence principle, which rule out linear couplings, at least for our purposes. Atomic clocks are dead, but they still tell you something. Quasar absorption lines, which give us strong constraints at low redshift, and then BBN, which gives us strong constraints at high redshift. We've already been able to say a lot, even just about the structure of the theory, like the fact that the theory has to be quadratically coupled rather than linearly coupled. And so this is maybe another way in which I'll just advocate for at least thinking about the models a little bit to know how to put all these things together and kind of establish a broader view on what is possible in this mix of theories.
So, does the oscillation also kill Oklo as a woman?
Yes. So, we talk about that. We can't derive anything robust from that. The other problem with Oklo is that so this is like some rocks in some abandoned uranium mine that had some nuclear reactions that we can use to constrain the fine structure constant like 10 or 100,000 million years ago, something like this, geological timescales. And that one's in a funny position where the duration of the reaction that is essentially being probed is kind of comparable to how long ago it was, and so now I can't really. Now I could have a happenstance cancellation of the scalar can be at the same point in its phase today as it was back then, and so that even further penalizes the bounds. And so actually very technically the posteriors become over the coupling become improper. You can't even normalize them because they fall off at large coupling, shallower than linearly. If you enjoy this pattern tree, it's all in our paper. But it kills Oklo as well. Yeah. Okay, great. So here's what we can say from all these probes. I glossed over, but nanograv is essentially just using pulsars as an accurate reference clock to compare a cesium clock to measure.
When you say it kills Oklo, you mean it kills the bounds from Oklo that's oscillating in nature, or what?
It kills the sensitivity. I have to marginalize over the possibility that the scalar just happens to be close to zero, and that is a steep penalty as a function of mass. That penalty as a function of mass happens to cancel out other mass dependence in the signal from fixing the fraction that the scalar contributes to the dark matter, and that's why these bounds are flat. So these two are clocks, one of them using pulsar timing arrays as a reference clock. This is university freefall, and this is another clock. I can only constrain gigantic couplings with my terrestrial probes. Quasars actually do remarkably well. So the way that we parameterize this theory is where these dimensionless coupling coefficients, these D's, measure the strength of the force relative to gravity. And so for the lightest masses, quasars can actually rule out sub-gravitational couplings. Again, this depends on the fraction of the dark matter that the scalar makes up, which I've chosen to be 1% to be compatible with the results I'll derive later. But yeah. So the upshot is that there's some territory in here where I've got some order unity couplings, or 10, 100, that are light enough, that are still light enough, and can still be strongly coupled enough to maybe give me a signature at the CMB. And so that's where I'm going next. Okay. So when thinking about recombination and its sensitivity to fundamental constants, the two coarse-grained things that I need to know are when did recombination happen and how quickly did it complete. As we all say, recombination is essentially, or the CMB is essentially a snapshot of the universe at the last scattering surface because of how quickly atoms recombine, and at which point photons freely stream to us from back then to the present day. To make these questions a little bit more quantitative, what we really want to know is what temperature did recombination occur. I know what the CMB temperature is today because we've measured it, and so knowing at what temperature recombination would have occurred tells me how long ago in expansion it happened. And then the second question, which was before how quickly did it complete, is really over how broad an interval do the CMB photons that we see last scatter. So like literally as a distribution over like a PDF over time, over some measure of time, how long ago did those photons that I see last scatter? Now it turns out that the electron mass has almost no effect on recombination when you measure it in the most relevant units. When I say most relevant units, I mean making asking questions about dimensionless quantities. I'll reiterate this on the next slide, but like the CMB, we're measuring we're measuring correlations of relative fluctuations over the sky, so in terms of angles. So there's no dimensions in that observation. So really, at the end of the day, I should only be able to constrain dimensionless quantities or ratios of dimensional quantities. And so the way that notion is manifesting in this plot is by, rather than plotting the visibility function, which is again a PDF, rather than plotting that as a PDF over time or over redshift, which includes a normalization of like the fact that I set the scale factor to 1 today. I just plot it as a function of the log of the scale factor relative to the moment of recombination, because that's the useful moment. Like that's the special moment for the early universe dynamics that I want to normalize my coordinate system to. Okay, so yeah, all of that, like the point of moving into these non-standard but dimensionless quantifications is that you can see that changing the electron mass has no effect on the ionization history, nor on the visibility. Whereas varying the fine structure constant has at least a visible effect. Whether it's a important effect remains to be shown, but it has a visible effect. In general terms, the reason for this is largely that the electron mass is the only mass scale on the problem, and so it essentially just sets the units for temperature, for instance. And so, like, if you just write out the Peebles equations for recombination, exchanging temperature for like temperature divided by the ionization energy of hydrogen, then the electron mass fully drops out. It's really just setting units. So that's why you see no difference here. When again, I choose smart units. And then for the fine structure constant, well, combination is messy. It involves a bunch of processes that have different powers of the fine structure constant, and so there's no reason a priori for all of those things to cancel out and give me the same result. And so yeah, so it modulates the rate at which recombination occurs, and that gives me noticeable differences in the visibility function, even when I center my coordinates and my scaling in the best way possible to remove as many effects as I can. Okay, that was a lot, a bit technical. Are there any questions before I go on?
I'm confused. So you have, we've got a KT associated with, for KT gamma associated with each one of these scale factors, right? And so we have that energy scale to compare to, compare to the energy scale introduced by the electron mass. So
I think maybe it would have been even smarter for me to have written instead of A over A star, T over alpha squared ME.
A star. Okay.
Yeah. So A star, everything with a star is evaluated at this point at peak visibility. So like when recombination happens. Yeah.
Okay.
Yeah.
Got it. Thanks.
Cool. Okay. So that's all just the process of recombination, but what about the anisotropies? This is the temperature power spectrum as a function of multipole moments, the usual thing. The best fit lambda CDM prediction with the data where the error bars are so small that they don't even breach outside of the size of the point that I chose. The usual story, there's like usual words that people say, usual story for the physics that governs the acoustic oscillations that give rise to the structure and the other relevant physical effects. And we usually use those to argue how this shape measures the baryon density and the CDM density. So now let me generalize this to a dimension, rather than those dimensionful densities. I'll tell you what the generalized dimensionless ratio is. So first, the relative heights of the peaks are controlled by the balance of pressure and gravity in the tightly coupled photon-baryon plasma. So rather than just measuring the baryon density, I have to augment in two ways. First off, it's the baryon density relative to the photon density, and moreover, it's that quantity evaluated at recombination. Not at the present day, because the present day is irrelevant to this calculation. The primary anisotropies get set in stone at recombination. Largely not to an extent that I can fully ignore, and certainly to an extent that will be important later, but for the sake of argument for how I measure these quantities, largely the present day doesn't matter at all. The universe that I live in is the universe with matter and radiation and nothing more. And so the only moment that's special is recombination, as indicated by the stars. So this is already like a parameter that people talk about. It's like this baryon to photon ratio R. Factors of 3 and 4 are motivated by the way things arise in the equation of motion. And likewise, I can apply the same logic to define a parameter that encodes the impact of the universe's transition to the matter-dominated epoch, which happens to occur shortly before recombination. And so there are some like broadband features in these acoustic peaks that come from like the influence of CDM potentials on the actual oscillations of the plasma, and as well as expansion history effects, which ultimately are governed by how long before recombination matter radiation equality occurred. So not how long equality occurred relative to today, but rather relative to the one special moment in the calculation, which is the moment of recombination. And so that's telling me about the ratio of the radiation and the total matter density evaluated again at recombination.
I mean, these quantities matter all through that history prior to recombination. It's just you can parameterize them in terms of them because we know how they scale.
Yeah, exactly. Yeah. It's not really one moment. It's just that within lambda CDM, I have a set in stone time dynamics for these two ratios, and so it suffices to specify their values at one moment. And so I choose the natural moment, which is recombination. Okay, so that's information that's just in the shapes. And like actually, if you look at what the measurements of these quantities are in a lot of cosmologies that traditionally yield different measurements of the baryon and CDM density because of degeneracies, the measurements of these two parameters remains robust. And I mean, this isn't like especially deep because like if you just write out like the tightly coupled system of equations, you can see that it's only in these combinations, again modulo Lloyd's point, it's only in these particular combinations that these parameters show up in the calculation. And so it makes sense that these are the more effective parameterization of. Okay, and then the last thing, which is the most important thing, is the second best measured number in cosmology, second to the CMB's temperature today. That second best number is essentially the measure of the angular correlation length of the photon distribution that we see, that we traditionally call theta sub s, which you can use trigonometry to write as a ratio of the photon sound horizon of recombination, so the distance that acoustic waves propagate up to the moment of recombination, relative to the distance from the last scattering surface that photons have to travel to reach us today. And so this ratio, I'll just note that the sound horizon bit can be calculated fully analytically, and it can be written in terms of my suggested parameters x equality and r star, and then that reveals that the only dependence that when I fix these things that encode the shape of the CMB, the only things that allow me to change the actual size, like the physical size of the sound horizon, are by changing the total radiation density or changing the moment of recombination, so the scale factor. And this is the thing that I have a knob for with the fundamental constants. All right, so here's the actual CMB calculation. I'm varying the electron mass by 15% in either direction, and I'm just fixing these three effective parameters that I've motivated in the last couple slides. And like, yes, there's like, I don't know, a dozen curves. They're all on top of each other for both the temperature and the polarization spectra. And this is just the primaries, so I'm not including the effect of lensing late times for those of you who might be wondering. But this essentially demonstrates that with like some like relatively simple arguments, there's just a handful of parameters that that if I fix those rather than say maybe the traditional ones that we think in terms of, it's very easy to get an identical CMB prediction even as I dial the electron mass. The same is absolutely not so for the fine structure constant for the reasons of the effect on the visibility function that we saw for one. And it turns out that the rate of photon diffusion from Thomson scattering at early times also is modulated by the fine structure constant, but not the electron mass. And so this leads to a altered damping on small scales, and then the effects of the broadening or contracting of the visibility function that I showed several slides ago essentially amount to boosting the amplitude of polarization on all scales, and then that eventually gets compensated for by suppression on small scales due to the same diffusive effects. And I can talk about the physics of that, but maybe for the sake of time, I'll just proceed and let you be content that these gigantic changes are not compatible with current data. Okay, so I'm going to return to the electron mass now. The punchline here again is just that I'm going to get like sub% constraints at 2 sigma on the fine structure constant just from CMB data, and that's the end of the story, more or less. But clearly, for the electron mass, I need something else. I need some other observable that's going to break this essentially rescaling symmetry that's relevant at early times when the universe is dominated by matter and radiation alone. And naturally, the thing that breaks that like rescaling of energy scales symmetry is the cosmological constant. And so now I've got to start thinking about effects at very late times. So the one thing that I can actually measure to constrain these models turns out to be the late time expansion history. And this is something that we have direct measurements of via cosmological distances, whether they be baryon acoustic oscillations, which are measuring the peak of the correlation function from acoustic oscillations in the distribution of galaxies, in direct analogy to the theta S quantity that I talked about for the photon distribution for CMB. And I can also do it with supernova distances. And so the extremely good measurement of that theta S number from CMB data essentially reduces this two-dimensional plane that I'm using to parameterize lambda CDM cosmology to a line, a one-dimensional line in this plane. And my measurements ultimately get governed by where. I should say I can move left to right in this plane, like along this one parameter line, by adjusting some things, but not all things. That's not directly encoded in this plot. But the perfect degeneracy achieved by the electron mass does allow me to essentially map this coordinate here, which maybe for the sake of time I'll gloss over, but I can absolutely explain it in more detail. But it turns out that the electron mass acts as the knob that I can use to move up and down this line. And so then I can use observations, for instance, from recent BAO surveys to break this degeneracy of this one line and select out some degree of electron mass shift. And the upshot here is that it turns out that there's a strong degree of discordance between current galaxy surveys, the colored ones, and the most recent supernova data sets that we have, which is in gray. This is not the Hubble tension. This is something new. This is like something that's become more and more manifest in data from 2024. It has, because of this strong degeneracy that is relevant for measurements of the early time electron mass, we end up getting very strongly discordant constraints or measurements depending on which of these data sets I choose to use.
Like I would move along the same degeneracy line if I was varying neutrino masses?
Yes.
Is the same? Okay, so
Yes.
the change in electron mass is totally degenerate with
Uh,
very much degenerate.
so this is-
change
this-
in neutrino mass.
So this plot is purely using probes of the expansion history.
Right. That's as far as geometric probes.
Geometric, yes. As far as geometry goes, that is completely true.
Okay.
And yeah, so the way you just spoiled the way in which I draw a connection to the neutrino masses, which is great because I'm probably running out of time. And I have this exact same plot, just with a different top axis that measures neutrino mass rather than electron mass variation. But yeah, maybe I'll get to that really quickly.
But Marlena just gave it talks.
Yeah, okay, so
I
you
knew
saw
what I
this.
would
Yeah,
do.
good, great. So then you're all experts and I'm wasting my time. Just kidding. Yeah, so here's, okay, so now, yeah, so historically, yeah, the things that Marlena told you about and that I can tell you about neutrino mass that you learn from looking at this plane and this composition of data, like I realized by working on this, but it's not just because of electron mass. Like the reason why the electron mass achieves this degeneracy is physically distinct from what neutrinos do as they become non-relativistic. But it turns out that hyperlight scalar fields, which recall I told you, must gravitate non-negligibly if I'm going to use them to mechanize these variations in fundamental constants to distinguish from ultralight. Turn out to be phenomenologically largely identical to massive neutrinos. So the idea is that the scalar remains, so this is as a function of scale factor, this is the fractional contribution of the energy density of different species, and the scalar just remains frozen until it eventually starts oscillating, and at that point it redshifts at the same rate as the rest of the matter, and so it essentially just boosts the matter density at late times meaning after recombination. And so that is effectively another knob that turns out to be a knob that allows me to explore this degeneracy direction along this white band. However, I don't have negative energy density in my scalar field, so I can't go this way. I can only go this way with the scalar field. However, the cool thing for this class of theories, I gave you theoretical motivation for this F5, this fractional contribution to the dark matter, being of the same order as the shift in the electron mass. And so it turns out that both of those effects, one, I expect them to be the same, the same order of magnitude, but it turns out that they can both compensate for each other, and so I can increase both of them simultaneously and stay at the same point in this plane. So that was cool because it's theoretical considerations that are that end up leading to a new degeneracy in CMB or cosmological observations. But of course, I don't have a detection or a discovery for you. Otherwise, you'd be more excited to hear this talk. And the reason for that is because of the effect of hyperlight scalars and, it turns out, massive neutrinos on large-scale structure. Just like massive neutrinos, hyperlight scalars do not cluster on only on very large scales do they cluster, so on most of the observed scales, they do not. And so they suppress the amplitude of structure by not contributing to that structure growth. And as you can see from the data superimposed, current measurements of the CMB lensing spectrum, a measure of large-scale structure at low redshift, the data seems to want even more lensing than in the case, even more structure than in the case of no contribution from the scalar field, no suppression at all. So that naturally translates to pretty tight upper limits. No matter what data set I combine my CMB data with, I get percent level upper limits on this fractional contribution of the scalar to dark matter. However, the different data sets, for the reasons that I motivated in the 2D posterior plot before, lead to wildly different measurements of the early time electron mass. So with the latest DESI BAO data that we've mentioned at the beginning, I get like more than a 2 sigma, like a 3 sigma-ish preference for a heavier electron mass at early times. I get slightly less of a preference from the prior generation of BAO data. But because supernova data prefer, it turns out, like matter fractions much larger than BAO data, because of this new like emerging tension that I told you about, supernova data actually prefer late recombination with lighter electron mass at early times. And so, depending on the data set, I either get, a pretty impressive alleviation of the Hubble tension, this is 71 plus or minus 1, or I get a Hubble tension that's, in spite of broadened error bars, still at the 5 sigma level, because I get a central value of like 62. And this is just by combining with different data set, different probes of the late time expansion history that only differ by their method, but not by the cosmology that they're probing. So that ultimately leads to a pretty messy parameter space plot for the electron mass. So for the photon coupling, for the fine structure constant, we turn out to get leading constraints in this mass range up to like very low masses where the quasars start to win. This coming from our CMB data and also BAO data, but that doesn't really change the results that much. And again, these are like near or sub-gravitational couplings. For the electron mass, things are a bit all over the place, precisely because of this geometric tension, and so I can't really, DESI actually gives me a measurement in this range away from 0, whereas some of my supernova data just give more traditional upper limits on the other side of positive or negative coupling. So hopefully the updated measurements that we'll get from DESI in a few months and in the coming years, as well as new supernova surveys that will be much larger in sample size and hopefully more coherent in their analysis and measurement methods and all that will resolve this current tension that propagates to the electron level here. Okay, so I clearly failed in my ambition to also cover neutrino mass in an hour. However, I basically said everything. So I'll just say that these results, everything that I said that I mentioned also applied to massive neutrinos, is really crucial to understanding this neutrino mass tension and this like negative neutrino mass business. That work ultimately, unfortunately, did not fully appreciate this geometric effect that was going on. That turns out to be the key effect that's leading new data to place, this new DESI data to give such tight constraints to the neutrino mass. So again, this is the exact same plot I've added in the Pantheon plus shoes data that is responsible for the Hubble tension just for illustration's sake. But now the top axis is neutrino mass measured in eV, and by comparing to the line of 0, you can see that DESI, this red, intersects with this white band from Planck down here in the negative mass territory. Of course, that doesn't make sense from like a theoretical point of view, but this is what's driving that constraint. And so just as electron mass results varied wildly depending on which data sets you use, neutrino mass measurements vary wildly as well, ranging from a upper limit from DESI that nearly rules out the not just the inverted but the normal hierarchy minimum mass, but to a marginal measurement like it's 2 to 3 sigma depending on some of the details. Measurement from our most recent supernova data set that is like slightly localized at masses around 0.15. Okay, yeah, thanks for indulging me on that. I'll stop there.
Questions for Zach?
Well, so how exactly will electron mass change the hypertension? Does it generate something like inflation slowly, or?
No, sorry, this is yeah, I guess I was pretty quick on that. So the electron mass allows me to make a combination earlier and make this scale factor at recombination smaller. I trigger recombination at a higher temperature when the electron is heavier, and by making yeah. So this gives me a way to shrink the sound horizon, and so if I like shrink this side of the triangle, and I also have to shrink this side of the triangle, and that means that I need to make the universe smaller, like in size and therefore more dense, and that means increasing Hubble. So it's that translation that puts me in this, yeah. Unfortunately, as convenient as this parameterization that I showed and didn't really explain in detail turns out to be, it doesn't let you directly see Hubble. But it turns out that going in this direction, which is what the electron mass being heavier does give you larger Hubble constants. Yeah. Thanks
So
for
it
asking.
change the result of the CMB measure of
Yeah.
the constant.
Yeah.
Okay.
Yeah. Yes. Thank you for having me explain that more clearly. Yeah. So that DESI data, which was blue, oh no, it was red. That's unfortunate. Yeah. That's what's giving you this measurement of heavier electrons and therefore higher Hubble.
So I only have a qualitative picture of this in my head, and I don't really know off the top of my head how strong some of these couplings are. But when I think about what happened if I changed like the electron mass of the fine structure constant, then I imagine like, oh, because of loop effects and normalization, I'm going to change muon mass. That also means I'm going to change like W and Z boson masses. I'm going to change quark masses. And I would think that you would have like cascading pretty non-linear, I guess, effects through like all the rest of the standard model. So are those things that we have to worry about? That if we turn one of these knobs, every other knob gets turned? Or are all those loop effects pretty weak?
Okay, so as far as loop contributions from electrons to things like the muon mass, the quark masses, like off the top of my head, I don't know, but these are like Planck suppressed couplings, and I would have to think that these would be very small effects, especially since we're in the territory of order unity or smaller dimensionless couplings. That said, so yeah, we do have some discussion to this effect in our new paper that is on HepPH right now, and like from a UV perspective, you certainly would expect more than just a coupling to the electron coupling. Absolutely. We kept our effective field theory point of view where you just write down whatever's possible and then constrain one coupling at a time. But like for instance, like I mentioned at the beginning that I didn't that I'm secretly only considering an electron Yukawa coupling and not a Higgs-Vev coupling. And that's because the Higgs-Vev does directly control the QCD scale, for instance, and contributions to the proton and neutron mass, and they're splitting. That does have important effects. That would have important effects on nucleosynthesis and the cosmological microwave background calculation. There actually was a paper that was proposing such a coupling to the Higgs bev as a model of varying electron mass, but did not account for the variation in the baryonic masses because they didn't appreciate how the Higgs bev ends up entering into the
Okay, so it's not that the electron mass itself is the field that is dependent on space, but it's coupled to some other scalar that's doing the work, and then this scalar is like Planck mass suppressed, and that's why we don't expect it to pop up very much?
Yes. Yeah.
Okay, that makes more sense, thank you.
Yeah.
So in this plot, I'm guessing, am I thinking right that the reason the BAO favor a higher electron mass versus the supernovae data is basically for two different reasons. I mean, I'm thinking the BAO measurements want a higher electron mass to suppress structure formation, whereas the Pantheon data want to suppress electron mass to increase H0. That right? These are two different phenomena.
Yeah. So this is good. I should clarify this. So the BAO data are just a measure of distances. So the input that they're providing is nothing about the amplitude of structure, but rather the co-moving distance, say, to particular redshifts from 0 to 2. And then when I say, I should have said this too, when I say supernova data here, I mean uncalibrated supernova data. That is, rather than using the Cepheids to calibrate the supernova so that they give me a particular H0, I'm marginalizing over that calibration completely, and that leaves me only with the measurement of the relative distances as a function of redshift, and that measures the shape of the expansion history. The shape of the expansion history is encoded by this vertical axis, which is the matter fraction, the fractional contribution of matter today. And it's that preference for a shape that is better fit by a larger matter fraction in supernova data that leads to a measurement of lighter electrons minus delta ME over ME, so lighter electrons at early times, whereas it's the preference for a lower matter fraction by BAO data, and especially the new DESI data, that yield a preference for heavier electron masses at early times. And this is just from the combination of the geometric information and the distance lab scattering with these direct probes of the expansion history.
So there's no F sigma 8 measurements in the BAO.
Oh yeah, no good, no.
Okay.
Yeah.
That's not what's pushing this.
Yeah.
I see.
Yeah.
Oh. Any other questions?